Welcome to this explainer. Today, we're diving into the absolute core of robotics. We're going to peel back the layers, moving from the raw physical hardware deep into the complex control algorithms that actually bring these machines to life. Whether we're talking about a simple weekend hobby rover or a multi-million-dollar next-gen humanoid, the fundamental principles driving them are beautifully connected. So let's kick things off with a pretty foundational question. Does a robot just react to the present moment, or is it actually predicting the future? It's kind of like our own bodies, right? We have senses to perceive the world, a brain to make decisions, and muscles to take action. To navigate a completely chaotic physical world, a robot has to master this exact same loop. All right, section 1, the sense, think, act loop. Underneath all the flashy carbon fiber and sleek designs, virtually every single robot out there shares this universal loop. Step 1 is sense, gathering data from the environment. Step 2 is think, where the robot processes that massive amount of data and comes up with a plan. And step 3 is act, which is actually executing the physical motion. This continuous, lightning-fast cycle governs everything from a little DIY line-following car all the way up to a highly advanced industrial manufacturing arm. If you understand this loop, you basically understand the heartbeat of all robotics. Let's ground this in the physical hardware for a second and look at the sense and act phases. Sensors basically act as the robot's eyes and ears. We're talking vision cameras, force and torque sensors for a really delicate grip, IMS used to track tilt and acceleration, and proximity sensors so the thing doesn't crash into a wall. On the flip side, actuators are the muscles. They translate digital commands from the brain into actual physical movement, whether that's through super precise electric motors, incredibly fast pneumatic systems, or heavy lifting hydraulics. Moving right along to section 2, inside the robot's brain. Right at the center of that middle think phase is the controller. Think of it as the robot's central nervous system. It's taking in an absolute avalanche of streaming data, extracting what actually matters, running it all through its programmed logic, and frantically firing off commands to those muscles. But how exactly does it make those decisions so incredibly fast? Well, it really comes down to two main algorithmic brains driving modern robotics today. Which brings us to section 3, PID, the reactive controller. Let's look at the industry standard first. It's elegantly simple, the PID controller. PID stands for proportional, integral, and derivative. The proportional term looks at how far off you are right this second. The integral term looks at past accumulated errors to fix those stubborn, steady biases. And the derivative term, that looks at the rate of change to dampen the response so it doesn't overshoot the target. The core philosophy of a PID controller is essentially asking, how wrong am I right now and how hard should I push back to fix it? Now you might be thinking, why on earth is this older, classical algorithm still everywhere in cutting-edge robotics? Well, PID dominates because it is computationally tiny and incredibly cheap to run on standard microcontrollers. It's also super easy for engineers to wrap their heads around and tune out in the field. Crucially, it doesn't even need a perfect mathematical model of the robot's dynamics. That makes it amazingly robust to messy, real-world uncertainties like friction or unexpected wear and tear. It really is the perfect engineering choice for low-level, high-frequency tasks, like just holding a wheel at a specific velocity or keeping a motor shaft perfectly stable. But, and this is a big but, what happens when a robot has to do more than just spin a wheel? What happens when a robotic dog has to balance on uneven, rocky terrain? Or an autonomous mobile robot needs to weave its way through a highly cluttered warehouse without hitting anything? PID really starts to struggle here because it's entirely reactive. It handles strongly coupled, multivariable systems pretty poorly, and it has absolutely zero concept of what happens next. That limitation leads us directly into section 4, MPC, the predictive controller. Model predictive control, or MPC, is a completely different beast. Instead of just reacting to the past and the present, MPC actually uses a complex mathematical model of the robot to predict the future over a short, finite horizon. It simulates all these different candidate actions, evaluates them against hard physical constraints, like actuator limits or dodging an obstacle, and then it chooses the absolute optimal sequence. It literally asks the system, hey, what will happen over the next few steps if I do this, and what is the best possible trade-off? It then applies the very first action and quickly recalculates the whole shebang all over again. So let's put these two paradigms head-to-head. On the one side, PID is reactive, computationally cheap, great for single variables, and focused entirely on correcting current errors.
On the other side, MPC is highly predictive, very compute-heavy, specifically designed for complex multivariable systems, and totally focused on optimizing future outcomes. To put it simply, PID corrects the present, MPC optimizes the future.
So where do we actually use these? Let's map it out. If you're just controlling a single motor or a robotic joint servo, PID is your winner, hands down. For the basic inner loop stabilization of a drone, PID is still the industry standard. But if you have an autonomous mobile robot, an AMR, trying to navigate a really chaotic factory floor, or a quadruped robot executing a mind-bendingly dynamic walking gait where balance and perfect foot placement actually matter, MPC is absolutely the right choice. It is truly amazing what predictive math unlocks for these complex machines. And this brings us to Section 5, the modern hybrid architecture. Here is the real secret sauce of cutting-edge robotics. It's not actually a cage match where MPC has to defeat PID. Real modern robots use a beautiful, layered stack of both algorithms working together. First, a high-level planner generates the overall route or the motion intent. Next, MPC handles the local feasibility, looking ahead to dodge an obstacle and making sure the robot doesn't violate its own physical limits. And finally, right at the bottom, PID loops are running at lightning-fast frequencies to actually stabilize the individual actuators and deliver the exact torques requested by the MPC. They work together perfectly. Now, I know what you might be wondering. Where exactly does artificial intelligence fit into all of this? A lot of people just assume AI is going to totally rip out and replace these classical controllers. But the source material tells a very different story. AI is augmenting classical control, not replacing it. Engineers are actually putting learned neural network models inside MPC to make the predictions better. They're using reinforcement learning to tune really complex walking gaits, while MPC keeps the robot from falling over. They're even using AI diffusion models to quickly generate candidate trajectories for the MPC to refine. Essentially, AI handles the messy, uncertain world, while classical control guarantees the physics actually work. Which brings us to a really great, punchy summary used in the industry to describe this exact integration. PID inside, MPC outside. You use MPC on the outside to handle the big, complex predictive planning, and you use PID on the inside for the fast, super reliable, low-level muscle control. It's kind of the ultimate engineering compromise. We've covered a ton of ground today, traveling from the raw physical sensors and actuators through the reactive math of PID, all the way to the predictive power of MPC. The marriage of physical hardware, classical control algorithms, and modern AI is unlocking capabilities we literally used to think were pure science fiction. So I'll leave you with this question to ponder. As AI models continue to merge seamlessly with predictive physical control, what impossible tasks will robots master next? Thank you so much for joining me for this explainer. Keep learning, keep questioning, and I'll catch you next time.